Hello, how are you friends? Welcome again to another episode. Today we hope you are going to learn something new that we have not taught in this channel. Last time we talked about pad footings. We looked at the types of pad footings that are existing, and we did the sizing of a basic pad footing. So this week we are going to look at the design of such a pad footing and all the necessary design considerations to make, how to size it from the plan dimensions to the depth to the reinforcement required, and how to carry out the necessary checks so that you design a safe pad footing. Welcome, and as we delve into this, we hope that you're going to learn, and we are going to greatly borrow from the British Standard BS 8110, the 1997 version, that is part 1. So I hope you're going to learn a lot. If you have a question or you realize something, you can raise it in the comment section. Otherwise, come with me as we study together. This was a project that we did somewhere, and I used this column to come and illustrate how you size and design a pad footing. So the very first thing, which is the very first step, is first of all to locate the column that whose footing you're designing, and in this case we are using column at grade intersection F9. That is the column that we're going to design the base for. I don't have the drawing here, but I hope you have understood what the F9 means. That means it's where axis F and axis 9 are intersecting, and a column at that place is the footing we are designing for. Actually, it is advisable you also design the column first. You get the reinforcement of the column, so that if the column is too slender or you have to make any changes, you design the footing while you have already known the column dimensions. So in this case, we designed the column, which I will present in the next video. But the column design was 300 by 200 millimeters, as we will notice as when we will be designing. So the very first thing you do is you get the loading from your structure, and we have been discussing the types of loads in structures, and we have GK and QK. GK is basically permanent actions. That means the dead loads on your structure. Dead loads are loads from permanent fixtures and fittings and the dead weight of the members. And then QK, this is the live load or the variable actions from the structure, and they are 59 kilonewton, as you can see. So you sum all of them just from the roof the way down up to the last column floor. So after you have obtained the total permanent actions and the total variable actions, the next thing you do is to sum them up, and I'm going to show us how to sum them up. There are two ways of summing loads. Actually, there are very many ways depending on the considerations you're making from the British Standard BS 8110. That is table 2.1. I think it's better we look at it. That is a 2.4.3. 2.4.3. The British Standard is open here, so we are going to use it. 2.4.3. We are almost right. We're there. Yes, values of loads for ultimate limit state. This is for ultimate limit state. Hope you remember when we were talking about ULS and SLS loads. So this is the table we use when we are combining our actions. And yes, we combined, first of all, we combined the SLS. These are the serviceability limit states, and I had explained this in the previous video. If you had not watched it, it's better you watch it before you watch this one, because it will give you an insight on what we are doing here. So you do 1.0 permanent actions or dead loads, add 1.0 multiplied by the variable loads. When you do that, you get 676.5 kilonewtons. And then for ULS, you use 1.4 GK and 1.6 QK, as we have already seen in the table. We have these for adverse it's 1.4, and for imposed it's 1.6 adverse still. So that is where we got those from, and this gives you 958.9 kilonewtons. So you list all of your loadings on the output. Hope you remember when we were going to size our footing from the previous video, we used the ULS loading. Now today actually you will notice that we will proceed to use the ULS even after using SLS for sizing of our pad footing. So the next thing you determine is durability and cover. This is easy to determine, and you first of all consider the conditions that the element is to be subjected to, and this being a footing, it could be that subjected to water, and probably it could be even at the point where we are doing our footing we are even below the water table, or it could be affected by water, or it comes in contact with water during rainy seasons, and even the soil when it's wet, it is going to affect our footing. So that is why we picked the condition to be severe, whose description is that the concrete surfaces, and in this case it's the footing, are exposed to severe rain, alternate wet and drying, or occasional freezing or severe condensations. These are actually what normal footings undergo. But when you're designing footings in soils with very high salts or in marine environments, there are codes for that, and you also pick a different condition. I think it is also better we go there. This is 3.3.1.2. Let's look at 3.3.1.2 so that we see how to get the conditions. Yeah, right there. Yes, 3.3.1.2. Really? Not supposed to be that. 0.4, sorry. 0.4 right here. This is 0.3, and then we have this is 0.6. So 0.4 is supposed to be here. And the table that we're using is the table 3.2, that is classification of exposure conditions, where mild conditions are concrete surfaces that are protected against weather and aggressive conditions, and these are probably things like the beams inside the structure and so on and so forth. And you also have moderate, severe, very severe, and all those, but we picked severe because concrete surfaces are exposed to rain, alternate wet and drying, or occasional freezing or severe condensation. Very severe, the concrete surfaces occasionally they are exposed to seawater. So you see, because here we have issues to do with the salts, and the salts affect our elements because once the salts get into contact with the steel inside the concrete, then it fastens up the corroding process, and as steel corrodes inside concrete, it expands, therefore it might lead to cracks and failure of our structural element. So that is why we put cover to our structural element, and in this case you realize we have chosen severe conditions. Now when we choose severe, you come to this table, or you look at the exposure conditions, and then you look at your lowest grade of concrete that you're planning to use, and then you can pick the type of cover. And here 50 is quite sufficient because it is not in a marine environment. If we could proceed, yes, that is 50 millimeters. Now the next thing after determination of the cover is estimating the planned size of the base, and this one we had done in the previous video, which I still insist that if you have not watched it, it's better you go back, watch it before coming to this one. So initially you're supposed to start designing this while you know your bearing capacity of the soil in that site. And this one you normally obtain them from geotechnical investigation, that is carried out on site by a geotechnical engineer. Though for sites with structures that are not so heavy, using experience and the soil type that you can observe from the site, you can estimate the bearing capacity. But again, if you have very high loads, high-rise structures, or structures probably more than 3-4 stories high, it's expedient to do the bearing capacity so that you're able to get the exact capacity of your soil. And in this case, this was once we excavated in the site, because this structure has already been constructed, we actually excavated up to a rock surface that was not it was we got to gravel, and then we were almost getting to a rock, and that is where we had our foundation. So 350 is a bit safe. And so to estimate the plant size, as we had talked in the previous video, you take the total SLS load and then you divide by the soil bearing capacity, and our total SLS load was 676.5 kilonewtons divided by 350 kilonewton per meter squared, and then when you do that sum, you get 2.26 meter squared. This is the plan area of your footing. So to get the plan size, you assume first of all the footing was square in shape, so you get the square root. That will give you 1.5 meters by 1.5 meters footing. And just allow me confirm that from my calculator. 1.5 by 1.5, it's 2.25. So 2.26 is not badly off. If we have 1.5, those are the dimensions of our footing. The next thing after getting the dimension of the plan area is you need to get the other dimension, which is the thickness of the footing, and this one you estimate depending on the loading you have and the type of axial loads you are going to experience, the type of supports, and your cover and all that. So looking at the loading we have, we assume the thickness of 400 millimeter, and then that is the H. When you read the British standard, H is normally the total depth or the total thickness of your concrete structure, and or rather pad footing in this case. So to get the effective depth, that is the D, as the codes call it. If you use Eurocode, it will be D, and then you will have a subscript here, EFF, to show that it's the effective depth, which is actually obtained by the total height or the total thickness of your footing, subtract the cover from one edge, subtract this is the diameter of the bar you plan to use, which you divide by 2. Therefore, effective depth is normally the depth from the surface of your concrete to the center of the main reinforcement that you're looking at. I don't know whether it's making sense. The top the topmost fiber, let me call it so, of my element to the center of the main bar I am using at that place. So if I'm planning to use 16 millimeter bars, the center is 8. That is why I'm doing 16 divided by 2. So that gives me 400 minus 50 the cover minus 16 over 2. And then I obtain 342 millimeter effective depth, which has been indicated here. Next, we determine the bearing pressure associated with ULS. Remember, we used SLS for sizing, and now we're going to proceed to use ULS to do the actual design of the footing. So the column axial load, as we had obtained it, it's 958.9 kilonewtons, and that is what we have listed here. What you do, you take the axial load, you divide by the plan area, the adopted plan area, and that will give you 426.2 kilonewtons per meter squared. So this is the ultimate design pressure that you're going to obtain on site under ultimate limit state conditions. Next, after obtaining that, now you need to start checking whether the thickness you chose is sufficient for shear forces or shear stresses rather. And sometimes, because reinforcement also contributes to resisting shear, sometimes we might just proceed with the reinforcement we assumed and determine the shear capacity and shear resistance of our section. But in this case, we are going to look at concrete first, so that it's always good you design for concrete to cater for shear, so that reinforcement only caters for bending moments. But there are cases where the concrete is insufficient in countering shear stresses. So in those cases, you bring in the use of shear links, which you design for, so that they can cater for the excess shear. So basically, when you look at shear, you use clause 3.5.5.2, which I would love us to go to. 3.5.5.2. 3.5.5.2. Almost there. Hope you are appreciating the Eurocode. Here it is. We are looking at shear stresses, and let's read it. The design shear stress V at any cross section should be calculated from equation 21. Equation 21 is this. This is V shear stress is equals to shear force V over B and multiplied by D. And we also have a disclaimer that in no case should this shear stress that we have calculated exceed 0.8 square root of FCU. This is the class of our concrete, or 5 newtons per millimeter squared, whichever is lesser among these two. The shear stresses are supposed to be always less than these two values, but sometimes that is not the case. That is why I said we use shear links, which we design for in that case. But first of all, we need to check, and if there is no need for shear links, there is no need to start designing for them. So whichever is lesser, that is the one our shear stresses are not supposed to exceed. And sometimes we have students who ask, here we are looking at shear resistance of solid slabs. This is not a pad footing, this is a solid slab. Then why are we looking at solid slabs and then we are using the formula in pad footings? This is the explanation. A pad footing is basically a slab that distributes my load from my column to my soil. So it is like a flat slab with a column. So you're designing it to be safe, so that the column does not punch through towards the soil, but it can efficiently distribute our loads towards the soil. Therefore, we can conclude that a pad footing is designed as a slab. Having said that, and I hope you have looked at how we have found that formula. So it's the one we have applied here. So we have taken our force, that is our loading, axial loading, and then here we have determined BD. B is the column perimeter. That is the one we have considered here, because our column was 200 by 300 millimeter. So we have gotten the perimeter multiplied by the effective depth. So B is the column perimeter, not diameter. Kindly note this. It is not diameter but perimeter. And D is the effective depth. So we found a value of 2.8 newtons per millimeter squared. And when we compare it with these values, this value was less than both of them. Therefore, our concrete footing is okay in shear. just at the face of the column. I'm interested to know the value that we have at 0.8 square root of FCU. So if I assume I'm using a concrete grade of 20 Newton FCU, so let me get the square root of 20. The square root of 20 is 4.47, and then you multiply by that by 0.8, you get 3.57. so this is less than 3.57. That means our column is safe against shear at the face of the column. And now we proceed. After we have obtained shear at the column face, we also have to determine punching shear at 1.5D from the column. Where did this come from? I want us to look at something here. Yes, this one. When you look at BS 8110, this is how we determine the effect of our shear forces from the column. And BS 8110 we use 1.5D from the face of the column. That is, we are going to experience high shear forces within this area. For Eurocode, we do the same thing, but we use 2D. And now, instead of using a rectangular area, we use a circular area. That is in Eurocode 2. But for ACI, we do it as we do in British Standard, but now we used to use 0.5D. This is also how you determine your column perimeters, but these are not applicable in our case because our column was not a square column, but it was a rectangular column. So that is why we used the manual or the analog method to get the perimeter. So kindly note that in BS 8110 we use 1.5D. In Eurocode 2 we use 2D. So if we determine the punching shear at 1.5D, this is the analog method that I've talked about, and let me explain it. 1.5 multiplied by D was 342 millimeters. Therefore I'm going to have one dimension. I'm going to have only this bit, so I need to multiply by 2 so that I can get this dimension and I get this one. And that is exactly what we have done here. That is why we have multiplied by these 2. And then I have added 0.3 because of the dimension of my column. So it is 1.5D multiplied by 2, add 0.3. Therefore I have this dimension, which is the length here. And I multiply by 2 because the length here is the same length here. Now I proceed to do this other direction, which is 1.5 times 0.34 multiplied by 2, again as I have explained. But in this case now we use 0.2 because the column dimension in this direction was 0.2 as opposed to the other direction where we had 0.3. So when you sum all these up, you get 2.65 plus 2.45, and this gives you 5.1 meters. That is the shear perimeter around our column. And then after getting that, you determine the area within the critical perimeter. So after getting that perimeter, you just determine the area at that section. And it's very easy because hope you remember this first one was a summation of this and that. So you divide by 2 to get 1, and then for this other direction you also divide by 2 to get the other. That is why you just take this, divide by 2, you get 1.325, and then you multiply by the half of 2.45, and that gives you 1.62 meters squared as the area within the critical perimeter. To get the shear force on the critical perimeter, you now take the ULS design pressure that was in kilonewtons per meter squared, and then you multiply the difference between the area of the planned area minus the area within the critical perimeter, so that you get the shear force that is going to be at 1.5d of our column, of our footing, sorry. So you get 268.5 kilonewtons, and this is now what you use to determine the shear stresses at 1.5d. This formula is the same one that we used here. So when you do that, you get 0.154, and then 0.154 is still less than this, because I remember we just calculated this a few minutes ago, and then it's also less than this. Therefore our footing depth and dimensions are okay in terms of shear, and we will not need to use any reinforcement or shear reinforcement to counter that. But I don't think we have looked at figure 3.16. I think we can go there so that we can observe figure 3.16. This is 3.11, 3.16, figure 3.16. Yeah, here it is, figure 3.16. yes. So you see, we get the perimeter just the way we have obtained it, and this LP is defined as 1.5d. Actually, when you read the code, if you read this BS 8110 and you read BS is it 5400 part 4, you will realize that this distance is normally it's a factor of 0.75. In this case we've used 0.15, but it must be a factor of 0.75. So note that, so that when you're designing using the British standard, you use a value that is a factor of 0.15. Yeah, so there we have our value. Now we proceed to after determining shear at the column face and at 1.5d, we proceed to determine the bending reinforcement that we need to use in our footing. So the first thing we do is the area of steel is given by the moment at the column face. You divide by 0.95 FYZ, and actually this is this formula is in clause 3.4.4.4, which I want us to look at just before we proceed, so that you appreciate the use of the British standard. 3.4. yeah, we're there. So that formula is right here. This is clause 3.4.4.4. It is for the design of rectangular beams, but it is the same clause we use when we determine the area of steel for almost many elements, including these footings, slabs, and these beams and all that. So this is moment divided by 0.95 Fy and then Z. So you can, wow, I've closed that. That was yes. So you can observe that is the formula. And then now to get the moment at the column face, you take this 426.2. Remember, this was the design ultimate. We can get it, it's here, ultimate ULS design ultimate pressure, that is 426.2 kilonewtons per meter squared. So hope you appreciate the use of this in the determination of reinforcement. So when you do that, you multiply by 1.5 and then by 0.65 squared over 2. How do we get this? This 1.5 is the total base length. Because this was per meter squared, we are multiplying by this so that we can get the total loading at the entire length of our base in one direction. And then you multiply by the distance, 0.65 squared. 0.65 squared is the distance from the center of the footing to the face of the column. So when we look at one dimension, let's look at the 0.2 dimension. When you look at the 0.2 dimension, the center half of 1.5 is 0.75. But when you look at the 0.2 dimension, 0.1 is on one side and 0.1 is on one side. So you'll get 0.75 subtract 0.1, so that you get 0.65, which is the dimension from the outer, how can I call it? From the edge of the footing to the edge of the column, in that direction. And for this we have also obtained the moment in the y direction. This is 0.6 because we are considering the 0.3 meter side of the column. So we use these two to obtain these moments, and we take the larger value, and that is what we're going to design for. So you determine k, and then k is determined by the formula m over FCUBD squared. And we can also appreciate the code k, it's right here, m over bd squared FCU, and that is what we have used. From k you also determine z, but for k it must be less than 0.156. If it is greater than that, then we have to include compression reinforcement. But since it's not greater, then we are only going to consider tension reinforcement, so that our footing is going to be singly reinforced. From there we proceed, we determine z, and the value of k we obtained here is the one we are going to use here to determine our z. And when you do the math using the formula still at that section of the British Standard, it's right here, you get 0.955d, which is greater than 0.95d, and we are normally supposed to use either 0.95d or lesser. So if this could have been less, we could have used it, but because it's more, we're going to use 0.95d as our z, which is the lever arm. So the area of steel will be given by the moment at the column face, which we have picked as the greater moment, then divide by 0.95. This is a factor that is found in the formula from the code, multiplied by this is the yield strength of our steel, and in this case we're going to use 460. But these days when you go to the shops, actually even over the counter or in hardwares, you can find one which has 500, but in this case we're going to use 460. Then you multiply by 0.95d. d was our effective depth. That gives you an area of steel required of 951.18 millimeter squared. When you get this area of steel, so you need to provide reinforcement that is going to resist this, and in this case we have provided 8 16 millimeter bars spaced at 200 millimeter center to center. This will provide an area of steel of 1610 millimeter squared, which is greater than this, therefore it is okay. After determining the reinforcement, now we proceed to find out the crack widths that we can experience in this section, and also carry out a check for cracking. For this we still using the BS 8110, and this we will use clause 3.12.5.4 and table 3.25 section C. But first of all, when you look at this, we have a clear distance of 200 millimeter center to center of our reinforcement, and this is less than 750 millimeters. Therefore, it is okay for such a section. We also consider tension reinforcement, as we will see from this clause. I think we can go there, 3.12.5. There is no need to cram all these things. If they are provided in the codes, just know how to use them and where to find them, so that you are able to design this with ease. Yeah, so this is table 3.25. When we look at the situation, we are talking about tension reinforcement, because we decided from our K value that we are not going to have compression reinforcement in our element, because we don't have excessive compression. Therefore, tension, we are going to consider C, which is the rectangular section in solid slabs. This minimum should be provided in both directions. Hope you note this, in both directions. Therefore, the definition of percentage is given by 100. AS is the area of steel you have provided, over AC is the when now it comes to the concrete one, the exact size of area of our element or member. And then when we look at the minimum percentages, we are using steel of FY of 460 and not 250, so that is where we use 0.13. To go back, you can see we have that formula there, and then when we apply it, we get 0.268, which is actually greater than 0.13, and this means that we have more reinforcement than the minimum. Therefore, it is okay when it comes to cracking. And therefore, the reinforcement provided meets the specified requirements by code for minimum area and maximum bar spacing in a slab. So remember, there is a time I mentioned that reinforcement help us to also counter for shear stresses. Lastly, after carrying out the cracking check, you also carry out a final check for punching shear, now considering the area of steel or the steel that you have provided. And this is the formula that we use, which is VC is 0.79, 100 area of steel provided divided by BD. You do that, you take them to power a third, and then 400 divided by D, you also do that sum. So if you substitute all those values, you will find a value of 0.45 newtons per millimeter squared. Therefore, this is the shear capacity of our element when we consider the reinforcement in place, and we also consider the concrete section and concrete depth. So therefore, punching shear, as we had obtained above, where was that? Here it was 0.154, which was actually less than these 0.45, which is the shear capacity of our pad footings when we consider reinforcement and concrete. Therefore, the depth that we picked is adequate, and our pad footing is sufficient against punching shear. So after all this, it's actually the final step in this lesson today, and I believe we have already the reinforcement we need. And you can see we only have the tension reinforcement, to mean this footing will only have bottom bars. There will be no top bars in our footing. That is because we don't have excessive tension or excess moments or too much compression on our element. And from there, we're going to also, you realize we've carried out the cracking check, punching shear check, shear at the face of the column and all that, and we have found our footing to be sufficient. Therefore, we proceed now to draw, and this is what you draw and provide in your working drawings or approval drawings for local authorities. So this is the plan view of our footing, and as you can see, we have you also need to name it clearly that we have a 300 by 200 millimeter column on 1500 by 1500 by 400 millimeter base. This was base B3 in our drawing, and they were 8 in number. And actually we designed using the critical column amongst all from all the 8. Therefore we're going to use this to provide reinforcement and use just the same base for all the 8 columns. And you can also observe we have 8 T16 02 tied at 200 mm spacing, and this is bottom 2. They are running in that direction. And then 8 T16 01 200 bottom 1, they are running in this direction. So this is how you do your plan. And we have also cut a section XX, which is down here. You can observe we have detailed 50 mm. I don't think it might not be feasible. Let me try to increase it. Yeah, so this is 50 mm. This is the blinding we do before we start fixing our reinforcement. And then you can see we have 01 as the bottommost reinforcement, that is bottom 1, and 02 as bottom 2. And we also have the total distance. Here we have indicated 1600. I think that is also not supposed to be the case. It's supposed to be 1500, so you can correct that. And once you also detail the section of a pad footing, you're supposed to show us just the starter bars of your column, so that because we need to tie them before we concrete, so that we know how many bars and how we are going to concrete them. So in this case we are going to have 6 16 millimeter bars on our column, and then we are going to have 8 millimeter links spaced at 150 millimeters. And once we get to the ground level slab, we're going to have an overlap of 800 millimeters. Hope you know how to determine this overlap. And we have done a video on that, on how to determine overlap on columns, beams, slabs, and all that. So you also need to indicate the overlap so that once we start tying this on site, you can even generate a bar bending schedule to help the those bending the bars and steel fixers to know the exact quantities and dimensions to use. And you also need to determine to indicate the depth on site. And because sites are not uniform, soils are not uniform, it is normally advisable that once they do excavation, you be there, or you as the engineer you direct on at what depth should they start casting their concrete pad footings. So I think that is all for today. It was just a simple class as you have observed it. To design a pad footings, the steps are very clear. First of all, you need to size it. Secondly, you need to determine the bearing pressure that is associated with your less, and then that is after, of course, you've sized all the dimensions, that is the plan and the thickness. And then you determine shear the column face and punching shear at 1.5 distance from the column. So once you do that, you also determine the bending reinforcement, because this will give you the reinforcement to tie. And if the reinforcement is in place, now you check for cracking of the section, and you now determine the shear capacity to find out whether your pad footing is sufficient in shear. And after that, you detail and go to site. So I believe you've learned a lot, and from today you have now understood how to design a pad footing and carry out the necessary checks. But I want to give you a challenge. Assuming our footing was failing in punching shear, and you have been tasked to provide a solution. They don't want to increase the entire depth. What should happen? One of the suggestions is you do a stepped pad footing, as we had discussed in the previous class. A stepped footing is one of the footings. So to do a stepped footing, you need to determine the punching shear, you need to determine the minimum depth that you are required to use at 1.5D, and you can step it at 1.5D so that you have more depth and it's more thicker towards the column. Another challenge I'm giving you is find out, of course I have mentioned, but find out what will necessitate us to use top bars in a pad footing. You realize this has only bottom bars. I have talked about it in this study, so if you cannot remember, you can replay it, and then you will realize I talked about it somewhere. Where do we or is it necessary to use these top bars? What necessitates its use? Of course, we use the bars to counter moments and shear. And for shear, if we need reinforcement, we are going to use shear links. But for the bars are meant to counter moments. So when do we have bars at the top? Which moments or what causes such a case? So you can think about those two, and you research from the BS 8110 and any other book that you are using, and I hope you're going to learn, and it will definitely help you. So thank you very much, and if you need any clarification on anything, you can this is a Kenyan telephone number that has been provided here. This is our office service line, so if you need anything, any clarification, you can always reach out to this number, and we will work together. Or if you have a site where you want us to come and confirm the sizes of footing or design the entire structure, you can contact us through this, or you can just in our YouTube channel, we have our email all over our videos, so you can also check that out, so that we help you on your site. Therefore, thank you very much, and may the good Lord bless and keep you. And I hope as you plan to design these footings, you're going to be careful, because if you mess here, you're going to have differential settlements and the likes, which will cause collapse of buildings. Therefore, be very careful, and always consult if there is anything that you think is you have not understood, or you don't know how to do it. We can do it for you, and we can provide consultancy and even construction services for your project. We are a licensed company with NCA in Kenya. NCA is the National Construction Authority, and we have the Reliquosite licenses to enable us to do construction works and these consultancy services. So feel free to reach to us. We also have registered professional engineers in our firm, and a number of graduate engineers who also help carry out these projects. Therefore, thank you very much, and may the good Lord bless and keep you. Adios.